Wish you a pleasant morning to everyone present here. So we are into the third session of this workshop, and then successfully we have finished session 1 and session 2 yesterday and day before. And now we are at the last lap of this workshop on the third session. As you know, we were discussing about the theories on artificial intelligence, then convolutional neural network, and also the implementation of a convolutional neural network in the last two classes. So now let us move on to the third session. So in this session, we will be discussing about the optimization. Yesterday, I made a mention about this optimization, though we didn't discuss in detail about the elements of optimization. Then we will look into the challenges in convolutional neural network and what makes us to adapt to deep learning. And then we will discuss about the research prospects in deep learning. How best we can extrapolate our learning on deep learning into the aspect of research. And the respective architecture. We also discussed on the sigmoid, tanh, ReLU, then leaky ReLU, the difference between ReLU and leaky ReLU, then softmax. Then we discussed on the challenges in neural network. Then I explained to you what is meant by convolutional neural network, the respective layers. And we ended the day one session by discussing about the popular CNN models around us. Then yesterday, I explained to you the working with the art of working with CNN with an illustration. Also, I explained to you how the layers are being organized and what is the purpose of each of the layer and why should we have those layers and how does each of the layer attribute to the final output that we are expecting from the model. So I illustrated the development of a model with the Cipher 10 dataset. And also we looked into the elementary coding aspects when you want to develop a model. Then we also had discussion about what is meant by overfitting, what is underfitting, and what makes a model to behave like a good fit. And also I just outlined about the regularization. Okay, so now let me start today's session with the essence of today's session with optimization. So we know what is meant by optimization. Optimization always aims to either maximize or minimize. So when we talk about computation, we try to minimize the computation, but when you talk about the accuracy, we want to maximize the accuracy. So depending upon the objective function that we define for any problem that we want to solve with optimization, so either we go for maximization or we aim at minimization. So that is what we exactly mean by optimization. All of us must be knowing about objective function. So we may have a single objective function or we can have multiple objective function. So when you have multiple objective function, one objective function may aim at maximization and another objective may aim at minimization and the combination of all these things. So let me just give a kind of quote about this optimization. The goal of optimization is to hit the sweet spots of maximum value optimization where foolish risk is balanced against excessive caution. So we aim to come out with the best possible solution at the same time, a feasible solution, assured that we have to have minimum computation as well as maximum accuracy or maximum optimization. So let us call what is meant by an optimization process. Optimization is a process of searching for parameters that maximizes or minimizes our function. So as I told you, so we are going to have a set of objective parameters that may try to maximize or minimize our function. So generally speaking, this machine learning or deep learning models usually may have indirect optimization. How are we going to measure the order of optimization? We normally use some metrics like accuracy or precision, recall, or confusion matrix, or we call it a sensitivity, all those stuff. So depending upon the matrix which are relevant for our problem solving, as well as the metrics that can contribute to our understanding, we must be able to choose the respective metrics, and then we have to indicate how well our model solves a given problem with reference to the metrics. Suppose if I talk about accuracy, then I try to maximize accuracy. If I aim to get the say mean square error, so the mean square error should be kept at bay. I have to minimize that. If I am going to have the metrics as say peak signal to noise ratio, so naturally I have to minimize that. So we have to decide, depending upon the nature of the metrics, it is decided whether we go for maximization or minimization. So here, like, let us indicate how well we can solve the problem. So on the whole, at the outset, so we can say optimization can be with respect to a cost function, for instance, to make you understand. So this cost function, we have to understand when you define a metric, when you define an objective, that is problem dependent, that is problem specific. Right? So suppose if I talk about a cost function which has to be minimized, then I can as well work with that kind of optimization. So talking about a problem, and when we talk about the workflow of a problem, optimization plays an important role. As all of us must be knowing, we work with heuristic algorithms and like bio-inspired algorithms, where optimization plays a very important and vital role. So when we talk about optimization, there are two major types of optimizations. One is first order optimization algorithms, and the second one is second order optimization algorithms. So what is meant by first order optimization algorithms? So these algorithms either minimize or maximize. As we know, a loss function, let us call in general as E of x, using its gradient values with respect to its parameters. So here, when we try to look into the accuracy, for instance, so at one point of time, the accuracy may increase, start increasing, and after certain, let us take for instance the epoch that we were discussing, number of iterations. And suppose if I start with the first iteration, the accuracy is say x. So as I increase the accuracy, then with respect to the epochs, the iterations, so the accuracy may keep increasing, right? So then after a certain point of time, when my number of iterations further a certain point is not going to help me to enhance the accuracy any further, so what will happen then? The iteration is not going to help me, so I have to fix the we have to fix the maximum optimization, like to say that I am going to get the accuracy in the best possible value, right? um, so like when you show you an example, you will be able to understand what is meant by this applying this optimization with respect to the gradient values. So when we talk about this optimization algorithms, they try to either minimize or maximize the loss function, and let us call in general as E of x by using its gradient values with respect to its parameters. I explained to with respect to accuracy. So the most widely used first order optimization algorithm is gradient descent algorithm. So one who wants to work with artificial intelligence, or to be very specific, with neural network or machine learning algorithms, or even convolutional neural network or deep learning, we cannot skip this gradient descent, because it is very essential to look into, because this is going to help us to fix the point where you get the optimized results. So the first order derivative tells us whether the function is decreasing or increasing at a particular point. So this is the ultimate thing. So it can be either first order, second order. Ultimately, we have to monitor the model to check whether it is giving the best possible result with best possible iterations. So first order derivative tells us whether the function is increasing or decreasing at a particular point. Well, so the first order derivative basically gives us a line which is tangential to the point on its error surface. So now we are going to just trace, if you talk about the loss function, then we must be able to fix a point where you get the best accuracy or best recall value or best sensitivity value, whatever it is. So you are going to fix a point, right, where from where we must be able to track back to reach the optimal solution where it is lying. When I show a diagram, you'll be able to understand little later. The second one is second order optimization algorithm. Second order method uses second order derivatives, which also this is otherwise called as Hessian. This is used to optimize in terms of minimizing or maximizing the loss function. So the Hessian is a matrix of second order partial derivatives. So let me not get into the partial derivatives. So all of us have the basic understanding about what is meant by first order derivative, second order derivative. So let us stop our discussion with that. So second order derivative provides us, so when you go for the second order derivative, it is helping us to work with a quadratic surface which touches the curvature of the error surface. So when you represent the error surface, then we must be able to locate, touch upon the curvature. That is where there is going to be a dip. So the dip is going to be taken, and from that point, we must be able to show how best we can arrive at or reach the optimal point. So before we move further into the gradient descent, I will explain to you what is meant by learning rate. So you have a set of inputs, and those inputs are to be given some weights. So the weights, when you are not able to get the optimal solution, then naturally we have to rework on the weights. Hope you will be able to remember. I had shown you a diagram with the back propagation. So what is back propagation? We try to go back to the neural network, right? We go to the previous layer, and then we try to uh, tune the weight, or we try to adjust the weight so that the learning becomes better and the results are promising. So in such cases, we have to keep updating the weights. So the learning rate we define as the quantity with which the weights are updated during the training process is called as step size or learning rate. So the order in which we try to modify that is being called as learning rate. So we must be able to understand what is meant by learning rate when we learn about optimization, when we try to use them on the convolutional neural network. Well, so suppose that the start of the gradient descent from say x0 is equal to 0.25. And you just understand this terminology gradient descent. Later I'll show you how this is being mapped. So suppose here you can see like there is a curve being shown. So it keeps going up. So between these 2 points that you see, there is a dip, there is a curve, right? So we must be able to reach that particular point, that is the middle of the dip. You have a curve, the bottommost line of the curve, right, between these 2 points. So what happens now? This model was learning and it was going up. And as you know, we are aiming at the value x, which is represented at the bottommost point of this curve between these 2 points. So I assume that, I understand that the optimal value of x is the point which is represented by the bottommost point of the curve. So what happens now? My model has gone beyond that point. So I have to make the model to come back to this point. I'm going to descend in the gradient. I'm going to climb down in the gradient. Gradient is going up. I'm going to climb down in the gradient. So now I can see in the next diagram. So I just come in, I just move towards the bottommost point in terms of steps. So this, the order in which we give the steps to descend down is called as learning rate. And depending upon the model that you're working with, depending upon the results that you get during the process of working on gradient descent, decides us whether we have to increment it in a faster pace or in a slower pace. So you can see the difference here. So here it is quite spaced. As we talk about the second diagram, it is quite spaced. Whereas as you take the third one, it is not spaced, it is very closer. So this is what we mean by learning rate. So suppose that we start the gradient descent from say x0 is equal to 2.5, right? So with the learning rate, we can call it as alpha is equal to 1, alpha is equal to 0.1, and alpha is equal to 0.01. So depending upon the learning rate that we give, then the steps with which the algorithm, the model, uh, is going to descend down matters. So when I give a bigger number, then it descends faster. When I give a smaller number, it descends slower by making very small incremental steps. Okay. So now, suppose when I take alpha is equal to 1, the sequence is practically oscillating between 2 points. When I give it as 1, for instance, so I may not be able to reach the point where I want to go. So it oscillates between the 2 points that I have given. So failing to converge to the local minimum, while for alpha is equal to 0.01, the convergence seems to be very low. So here we have given 3 diagrams. So the first one is for alpha is equal to 1. The second one is for alpha is equal to 0.1. The third one is for alpha is equal to 0.01. So with this understanding, you can understand um, like try to understand the learning rate this way. Now I have got a pattern of the model being plotted. So for each and every kind of curve that I have, I can come out with, I mean, when I take this entire diagram, I can come out with two different quantities. One we call as local minimum, the other one we call as global minimum or global maximum or local maximum, depending upon your objective function. So those who have already worked with particle swarm optimization will be able to understand this local minimum, then global minimum, local best, global best, like that. Well, so my aim is to come down to the local minimum, that is the point which is at the bottommost point of the curve. So when I give alpha is equal to 1, it just oscillates and I'm not able to reach to that particular point. But whereas when I give this alpha is equal to 0.1, so it descends down in an incremental phase. It is in a spaced manner, and then I'm able to reach. And when I give this as 0.01, we can see here the process of convergence is very slow. So it is not able to converge faster. So what is our total understanding over here? Here the main idea is, so depending upon the learning rate, right, the convergent process takes place, but there is no hard and fast rule to decide about the factors for learning rate or decide about the quantity for learning rate, because it is decided by the nature of the convergence, the nature of the problem we have, the nature of the data set we are handling, and the like. Okay. So here in the bottom, we have seen the number of steps are being given and the value is being taken. So here you can understand what happens when you give this learning rate. LR stands for learning rate. When LR is equal to 1, what happens? When LR is equal to 0.1, what happens? When LR is equal to 0.01, what happens, right? So that makes us to understand how the learning rate takes place and how best are we able to reach the minimum point. So I think from this, you'll be able to understand better. So what is meant by this gradient descent, right? So before we get into theoretical aspects of this, let us look into the diagram that is given on your right bottom. So here you can see there is a U-shaped curve in blue color. So now from this, you can understand. I have got weights being plotted here. You can see here, weights are being plotted. One second, I'll just move this tab so that you'll be able to. So you can see here the weights are being plotted here, and on the y-axis we have got the cost function. So what is the cost function for the respective weight? So now this diagram explains to us what will be the cost incurred for the respective weights, right? So so as you start from the bottom, from 0, as you try to increase the weight, there is some plot being done with respect to the cost. So in the x-axis we have the weights, in the y-axis we have the corresponding cost. So what happens here? So when the weight is very less, the cost is very high. So as we try to increase the weight, the cost comes down, and after certain point of time, so when we try to increase the weight all over again, then it starts, the cost starts increasing. So this is what we call as gradient being established, right? So now what do we understand? So here, as the cost is increasing, despite we increase the weight, it is not going to serve us any purpose. So with respect to this diagram, so we know that the point where at the bottom, which is being shown as J min of W, that is the point where you get the minimum cost. J min of J stands for the cost function. So J min of W. So this is the point. You can see here, this is the point which is going to give us, 1 minute, I just pull my mouse pointer. It has gone somewhere. Okay, so here, so this is the point which is going to help us to understand the weight chosen at this point will give us the minimum cost, right? So you can understand. So this is J min W's cost. Okay, so we call this point as the global minimum cost. Now we must be able to descend in the gradient. So this is the gradient. We are going to descend in the gradient. So now we are going to draw a tangential point, right? So in the previous first order derivative, we discussed about this. So we are going to draw a tangential point. So now it is going to touch on the gradient. So this is the point from where we start the learning rate. We start the process of gradient descending. So this is the point where we have to decide about the learning rate. So if it is very close by, then you can choose the learning rate to be comparatively minimum, and if it is quite far off, then we can choose it to be comparatively larger. Well, so from this point, we have to initialize the weight. Then with respect to this weight, we have to decrement the weight so that we can reach this point where the cost function is minimum, right? So this is what we mean by gradient descent process. So in the gradient, we know where is the minimum weight, optimal weight, and for which we get the optimal cost factor. And now suppose if your model is somewhere here, then from this tangential point, we have, this is the initial weight that we initialize, then we try to decrease the weight, and hence we are able to come down. Okay, now let us go to the next one. So here, as we take this, there are a lot of curves like this. So for each of this, as I told you, we can fix the local minimum, local maximum, global minimum, global maximum. So if we try to come out with minimum and maximum for the entire model, so that is your global minimum and global maximum. Suppose if we have a lot of curves, then for each of the curve, we can decide about the local minimum and local maximum as it is shown here. Okay, so what do you mean by this gradient descent? So this gradient descent is a very popular and widely used optimization algorithm, which is mainly used to find the minimum of the function. That is, we try to find what is the minimum value for a given cost function, for instance. So in machine learning, gradient descent is used to optimize the parameters in the model. We try to optimize here. Suppose when I'm going to use the weight for with respect to gradient descent, I will be able to find what is the optimal weight. So then parameters can vary according to the algorithm, such as like it can be suppose when we talk about linear regression, or when you talk about neural network. So depending upon the type of the algorithm that we use, depending upon the type of model that we use. See, when you learn about machine learning, I made a mention about supervised learning and unsupervised learning. So as you take supervised learning, you have got a lot of algorithms. As you all must be knowing, like linear regression, logistic regression. Then there are a lot of algorithms, right? So we have support vector machine, then we have naive-based classifier, decision trees, and we have good amount of algorithms. So with respect to each of the algorithm, we have to decide about what is the parameter to be optimized. So like I cannot blindly just apply the optimization that I use for linear regression to logistic regression and vice versa. So the optimization that we think and then apply for a model is highly specific to the model, and the optimization process cannot be generalized. Well, so the parameter can vary according to the algorithm. So depending upon the coefficients, suppose when we take linear regression, we work with respect to coefficients, because you know y is equal to mx plus c. So there you have to you should try to optimize. If y is equal to mx plus c, and we sometimes call it as ax plus c, y is equal to ax plus c. And here a is the slope. So now we try to optimize the slope value, the a value. So in the case of linear regression, we try to optimize the coefficient, whereas in the case of neural network, we should try to optimize the weights. So now you understand, for each of the model, we have vital parameters. So we try to optimize with respect to those vital parameters. Then the inclined or irregular is the cost function. That is here in this case, in the second diagram, it is in the case of U shape, and in the first one, it is in the case of sine wave. So depending upon the kind of pattern the model generates, and accordingly you get the pattern. So it is getting plotted, and we are able to visualize the kind of cost function that is being got. Well, the role of gradient descent algorithm, this is going to provide the direction and the velocity. So in what direction do I have to descend? Do I have to descend or do I have to climb? So it can be either descent operation or ascent operation. So now it has to provide the direction in which the algorithm has to move. In addition to that, it has to give the velocity. So now you know the velocity. So suppose if you target to throw the ball on the wall which is opposite to you. So if it is very close by, you just throw it slower. If it is very far off, then you push it harder and then you give with good amount of force. So like this, depending upon the place where we have to reach to converge, and accordingly we have to decide about the learning rate. So the learning rate can be slower or faster as decided by the nature of the problem to be solved. So, and the velocity, what is velocity? It is the moment in order to attain the minima of the function where the cost is minimum. Right? So we try to get the minimum weight possible. Well, so this again will help us to understand this gradient descent. So here you have the weight and then you have got the function and E. So we calculate E. So you can see here a red color dot is there, then arrow marks are there. So if we are on the right side, then we have to descend towards the optimal W. If you are on the left side, we have to move towards this way. So which direction do we have to move? It is decided. So this image shows the process of weight updates. So every time when you move down, what happens? The weight is getting updated. So let us assume I descend down from the right side curve. So what happens? The weight is getting reduced because suppose when I take the weight here, say with respect to the first red point, say 50. And when I come here, it may be 40, then it may be 30. It is getting reduced. Whereas if I try to work on the left side, for instance, so what happens now? The weight is getting incremented. So depending upon the direction, the weight is getting either incremented or decremented. So you understand, right? So if it is from the right, when you talk about the right side curve, we decrease the weight. When you talk about the left side curve, it is getting increased. This is a very common understanding. So here, so the image shows the process of how weights are getting updated, how the weights are getting either decremented or incremented with respect to the opposite directions. So here, this speaks about the weights that we give for the network, for instance. So here we have a function, E is equal to, right? It can be an error function, it can be a cost function, as you like. So here you can calculate with respect to this formula. Let me not get into the formula, and because it's very easy for you to understand. And the wi, xi, the weights, and then y is the output. We apply that and get it. Here, this U-shaped curve is called as gradient. That is representing the slope of the cost function, or it can, on some occasions, it can be the slope of the error function. So, if weight values are too small or too large, then large errors may occur. So, suppose if we try to have a very fast learning rate, probably we may not be able to reach the point of convergence. We may try to go beyond that. So, it's very important to decide about the learning rate and how the weights are being updated. We have to have a good care about the pattern in which the weights are being updated. So it can descend downwards in the opposite direction in order to reach the local minima, and it can be from either of the side of the curve. So what are the variants of this gradient descent? And this gradient descent can also be viewed in the form of this gradient descent with momentum. So there it was a U-shaped curve, and here it is in the form of oval shape. So now when I suppose if it is here at the bottommost side, then what happens? I must be able to reach the inner part where there is a local minimum. So I must be able to have a good amount of hops by means of which optimally I must be able to hop to reach the minimum point. So this is an illustration for momentum. And there is one more thing called RMS prop Adam, and you can just Google and find out. Here I have given the link which speaks about the principles of RMS prop as well as Adam. So the only thing that I want to highlight here is what are the tips that we have to keep in our mind when we are working with gradient descent. Here, it's very important to first plot the cost versus time we can do, and we can plot the cost versus weight, and then we have to decide about the learning rate. What is the order in which we want to descend in the gradient? then we must be able to rescale the inputs. Suppose if the data set is not able to give us proper learning, so we must be able to either augment the learning, augment the data set. What is meant by augmenting? We have to increase the number of images or number of data in our input data set. So then we may try to work on the number of passes, the kind of epochs that we do. Then we can go for plotting the new cost with respect to the parameters, and then we try to see how best our fine tuning of the model works well. So now let us more attention towards what are the challenges in convolutional neural network. So I told you this convolutional neural network always gives the best results in terms of image handling and any kind of operation that we do with images. It can be for computer vision, like image recognition, image identification, image classification, then object recognition, object identification, all those stuff. In such cases, now we have to work with images. Now, the point is like as we talk about any kind of image data set, or it is highly applicable for any data set we talk about in terms of machine learning, deep learning, convolutional neural network. We have to keep in our mind there are two aspects that govern the quality of the data set. So the one is we call as distribution of the data set, and the second one is the diversity or the variability of the data set. What do you mean by distribution? So let us assume that we have seen an example of the cipher 10 where we have got 10 different classes, say aeroplane, say dog, cat, horse, all those things. So let me imagine I'm going to, let me decide to develop a model to, to identify whether the given image is a horse or not. Well, so what am I supposed to do? I have to first collect the images of hearts. It may be say 100, 200, 300. I have to collect the images of hearts. And when I'm collecting, I have to ensure that my data set should be a very good representative of horses of different kind, horses of different age, and horses of different shape. I mean, it can be like a very a strong hearts or very puny hearts and all those stuff, because each and every